This is an AQA past paper solution. We are going to solve the exact questions that appeared in the exam paper.
Yeah, that is our entire mission for today. We are doing a deep dive into the GCSE Physics 8463 for 1H.
Specifically, the June 2024 exam paper.
Right. We have the authorized mark scheme right here.
And we're going to walk you through it. So just so you know how this works, we are proceeding question by question.
We have the questions from the slides on the left side and the authorized solutions directly on the right side.
Okay, let's jump straight into slide 2. This is question 1, focusing on energy stores and environmental impact.
Right, so question 1.1 and 1.2 are about identifying energy.
The first scenario is simple. Water is being heated. They want to know which energy store is increasing.
The mark scheme specifies thermal energy, or internal energy.
But I see here they also accept the kinetic energy of the particles.
Yeah, they do. Now, the second scenario is about water being pumped uphill.
Uphill being the key word there.
Exactly. Because it's moving uphill, the energy store increasing is gravitational potential energy.
Or GPE.
Right. Moving to 1.3, we have to compare two methods of storing energy, method A and method B.
And it specifically says including calculations on the slide.
You have to do the math to get the marks. Let's look at method A. It increases the water temperature. The slide shows we start with 33,600 kilojoules.
But the efficiency is only 60%.
So we need the useful energy. You calculate 33,600 multiplied by 0.60.
Which comes out to 20,160 kilojoules.
Now for method B, pumping water, the starting energy is 490 kilojoules.
With an efficiency of 75%. So 490 multiplied by 0.75 gives us, 367.5 kilojoules.
Right. So the comparison you need to write down is that method B is more efficient. 75% compared to 60%.
But method A actually stores significantly more energy per 100 kilograms, over 20,000 kilojoules compared to just about 367.
Spot on. Section 1.4 asks for ways to reduce carbon dioxide emissions. One for transport, one for generating electricity.
For transport, the solution suggests using electric cars, walking, cycling, or public transport.
But you have to give the reason. The reason is that it reduces the burning of petrol or diesel.
Okay, and for generating electricity.
You suggest renewable methods, nuclear power, or even just reducing demand by turning off appliances.
And the reason there is that it reduces the use of coal, oil, or gas.
Exactly. Let's turn to slide 3. Question 2. Nuclear fission and power.
We have a diagram, figure 2, and we have to complete some sentences about the fission process.
The first sentence is about what happens when uranium splits into two parts. It releases what?
Neutrons. The slide clearly says neutrons.
Right. And the second sentence states that the process releases electromagnetic radiation in the form of
gamma rays.
Easy marks if you know the facts. Now, 2.2 asks for the equation linking energy, power, and time.
That's E equals P times T.
Now, we use that in 2.3. We need to calculate the energy. The power is given as 500 megawatts.
You have to be careful there.
You really do.
Yeah.
You must convert 500 megawatts to watts. That is 500,000 watts.
So, 500 million. And the time is 3,600 seconds.
So you multiply 500 million by 3,600.
That gives a huge number. 1,800 billion joules.
Or 1.8 times 10 to the power of 12 joules. Standard form is much easier to write.
Definitely. Question 2.4 asks for valid safety precautions for radioactive waste.
The mark scheme has a few acceptable answers. You can say, bury the waste, use cooling ponds, store it in secure vessels or metal containers, or cover it in concrete.
Just one of those is enough. Okay, 2.5 is an operational time calculation. The plant operates for 92% of a year.
This is straight math. 92 divided by 100 multiplied by 365 days.
Is 335.8 days.
And the mark scheme says you can accept 335 or 336 as well.
All right, moving to slide 4, question 3. We are looking at a resistance practice.
This requires a level 3 method description. They want to know how to find the resistance of a wire.
So you start by measuring the length of the wire between the crocodile clips using a ruler.
Then you measure the current with an ammeter and the potential difference with a voltmeter.
Next, calculate the resistance using the formula R equals V divided by I.
To get a range of data, you have to explicitly state to vary the length by moving the crocodile clips.
And then repeat the readings and calculate a mean.
Right. But don't forget the safety and accuracy points for full marks. You need to keep the current low to minimize heat.
And switch off the circuit between reading.
Yes. Okay. 3.2 asks you to identify the correct graph for a wire at a constant temperature.
The slide shows it's the bottom graph, the straight line passing right through the origin.
Because resistance is directly proportional to length at a constant temperature. Finally, for this slide, 3.3. Why is the 1.50 volt cell not a hazard?
Simply because the potential difference is very low. So there is no risk of electric shock or electrocution.
Let's flip to slide 5. Static electricity. Question 4.
We have 4.1. The classic hair standing up on a Van de Graaff generator. We need to explain why.
It's a sequence. First, electrons are transferred to the student,
Which means the hair becomes negatively charged.
and crucially, each hair has the same charge. So, like, charges repel. That's why they stand up.
Question 4.2 asks the definition of an electric field.
It is the region around a charged object where another charged object experiences a force.
Next, 4.3 asks for the trend in field strength.
Field strength decreases as the distance from the charged metal dome increases.
Then we hit a calculation in 4.4, finding the potential difference.
We are given an energy of 0.60 joules and a charge of 2.0 microcoulombs.
There's that prefix again, micro.
You have to convert it. Q equals 2 times 10 to the power of negative 6.
So the formula is energy equals charge times voltage. We substitute the values. 0.6 equals 2 times 10 to the negative 6, multiplied by V,
Rearrange that to find V. It's 0.6 divided by 2 times 10 to the negative 6.
which equals 300,000 volts.
A big spark. And 4.5 asks what change would increase the distance that spark can jump.
The correct answer on the scheme is a decreased electrical resistance of the air.
Moving on to slide 6, question 5, mains, electricity, and circuits.
Question 5.1 is factual.
Mhm.
What is the main supply?
The frequency is 50 hertz and the potential difference is 230.
5.2 is a resistance calculator. The power is given as 340 milliwatts, and current is 0.75 amps.
Convert the power first. 340 milliwatts is 4 watts.
We use the formula power equals current squared times resistance. So 0.34 equals a 0.75 squared times R.
Rearrange to solve for R. That's 0.34 divided by 0.75 squared.
And the resistance is 0.60 ohm.
Now 5.3 is an interesting one. Why aren't dirty coins recognized by a vending machine?
The dirt changes the measured resistance of the coin. Or you could say the resistance is different from what is expected.
5.4 asks for the circuit symbol for a thermistor.
You just described the rectangle with a hockey stick line passing through it.
Right. And 5.5 is a thermostat circuit calculation. We need to find the potential difference across the thermistor at 20 degrees Celsius.
Step 1, we read the provided graph at 20 degrees Celsius. The resistance there is 80 ohms.
Step 2, find the total resistance. We have a fixed 400 ohm resistor, plus the 80 ohms from the thermistor. That's 480 ohms total.
Step 3, calculate the current. I equals V divided by R. The voltage is 12, so 12 divided by 480.025 amps.
Final step. Find the potential difference across just the thermistor. V equals I times R, so 0.025 multiplied by 80.
Which gives us 2.0 volts.
Perfectly stepped out. Okay, slide 7. Forces and elasticity. Question 6.
6.1 asks what energy store is involved. It's elastic potential energy.
6.2 is a big calculation for maximum height. We have a bungee jumper on cords.
First, calculate the elastic potential energy for one cord. E equals 0.5 times the spring constant 735 times the extension 8.0 squared.
That gives 23,520 joules for one cord.
But the slide specifies there are 2 cords. You have to double it.
So total elastic potential energy is 47,040 joules.
We equate that to gravitational potential energy to find the height. 47,040 equals mass times gravity times height.
The mass is 240, gravity is 9.8, so 47,040 equals 240 times 9.8 times 8.
Rearrange that. H equals 47,040 divided by the result of 240 times 9.8.
And you get a height of 20 meters.
But then 6.3 asks why the actual height is lower.
The authorized answer is that air resistance opposes the motion, or that energy is dissipated and transferred to the surroundings, so the efficiency is not 100%.
Makes sense. Let's look at slide 8, question 7. This is all about density and measurement.
7.1 identifies an error type. The student's eye is not in line with the water level.
That causes a random error.
7.2 asks about the string used to lower an object into the water. The student used thick string.
The mark scheme says thin string would be better because it displaces less water, which affects the volume measurement less.
7.3 is about the measuring cylinder's accuracy. Why is it inaccurate?
Because the resolution of the cylinder is too low. The slide notes the resolution is 0.2 cubic centimeters.
7.4 deals with an electronic balance reading of 0.02 grams when empty. How do you use this reading?
You have to subtract 0.02 grams from the measured value. It's zero error correction.
Finally for the slide, 7.5, a mass calculation. We have a density of 21,500 kilograms per cubic meter and a volume of 0.44 cubic centimeters.
Watch the units. We have to convert the volume to cubic meters. 0.4 cubic centimeters is 4.4 times 10 to the negative 7 cubic meters.
The equation is mass equals density times volume.
Substitute the numbers. Mass equals 21,500 times 4.4 times 10 to the negative 7.
And the answer is 0.00946 kilograms, or 9.46 times 10 to the negative 3 kilograms.
Okay, slide 9. Question 8. Gas property.
8.1 asks to explain why pressure increases when a plunger is pushed in a blocked syringe.
When you push the plunger, the particles are closer together, meaning the volume decreases,
Because of that, the frequency of collisions with the walls increases.
which creates a larger total force on a smaller surface area. That explains the pressure increase.
8.2 asks about the effect of an increase in temperature on the gas.
An increase in temperature means the mean kinetic energy of the particles increases.
Now for 8.3, a temperature calculation.
The energy is 0.0130 joules. Mass is 2.60 times 10 to the negative 8 kilograms. And the specific heat capacity is 1.01 kilojoules per kilogram degree Celsius.
Convert the specific heat capacity to joules first. So C equals 1010 joules per kilogram degree Celsius.
The equation is energy equals mass times specific heat capacity times temperature change, or delta theta.
We substitute what we have. 0.0130 equals 2.60 times 10 to the negative 8 multiplied by 1010 multiplied by delta theta.
Rearranging for delta theta gives us 0.0130 divided by the product of 2.60 times 10 to the negative 8 and 1010.
And that calculates out to exactly 495 degrees Celsius.
Moving right along to slide 10. Question 9. Radioactivity.
9.1 asks us to identify a radiation source. Source A is alpha.
And the reason given on the slide is that the radiation travels approximately 3 centimeters in air, and then the count rate drops to the background level.
Because alpha has a very short range in air.
9.2 asks how to test for absorbing material between beta and gamma.
You use an aluminium sheet. The beta radiation will not penetrate. It gets stopped, while the gamma radiation will penetrate.
Next, 9.3 and 9.4 come for safety precautions. First, for dose, then for contamination.
To reduce the dose, you increase your distance, limit the time of exposure, use tongs, or wear a lead apron.
And to prevent contamination.
Wear gloves, a lab coat, and do not touch the source with bare hands.
Okay, 9.5 is an activity calculation.
The method requires a tangent drawn on the line at 300 seconds.
From there, you calculate the gradient from the tangent. Change in y divided by the change in x.
The answer they are looking for is 7.1 times 10 to the power of 20 becquerels.
Though the mark scheme allows a range between 6.5 and 7.6 times 10 to the 20.
We are on the final slide, slide 11, question 10, domestic electricity.
10.1. What is the insulation color of the live wire?
It's brown.
10.2 asks for the fuse symbol.
That is described as the rectangle with the horizontal line passing through it.
10.3 is a current calculation. We need to find the current if 2.0 coulombs flow in 400 milliseconds.
First, convert the time to seconds. T equals 0.4 the other 0 seconds.
Then use I equals Q divided by T. So 2.0 divided by 0.40.
Which is 5.0 amps.
10.4 is a mass calculation. The energy is 1.02 joules, and the latent heat is 60 kilojoules per kilogram.
Convert the latent heat. L equals 60,000 joules per kilogram.
The formula is energy equals mass times latent heat. So 1.02 equals mass times 60,000.
Mass equals 1.02 divided by 60,000.
That gives a mass of 1.7 times 10 to the negative 5 kilograms.
And finally, 10.5. What is the effect of energy transfer to the surroundings on the time it takes the fuse to melt?
The mark scheme says the time would increase.
Because more energy needs to be transferred in total to compensate for the loss to the surroundings.
And that concludes our deep dive into the June 2024 physics paper.